Now we can talk about circles. A circle is a set of all points equidistant from a fixed point called the center. So here's an example of a circle. Point A is on the circle. Point B and the center are inside the circle or within the circle. So it's very important to understand the distinction of on the circle versus inside the circle. A segment from the center to any point on the circle is called a radius, and the plural of that word is radii. All radii of the same circle have the same length, by definition. The length of the radius is abbreviated as r. A segment with two endpoints on the circle is called a chord. Different chords can have different angles and different lengths, so FG is a relatively short chord, EH is longer, and DJ, that goes almost all the way through across the circle, so that's a much longer chord. There is no shortest chord. The chords can be anything down to 0, but the longest chord is a chord that passes through the center. A chord that passes through the center of the circle is called a diameter. So a diameter is a chord. In fact, it is the maximum length chord, the longest possible chord. And notice that a diameter is made up of two radii. KO is a radius and MO is a radius. So we can say diameter equals 2r. The length around the whole circle is called the circumference, denoted by C. The ratio of C to D is one of the most special numbers in all of mathematics, pi. So C equals pi times D, circumference equals pi times diameter. And we could also write that as circumference equals 2 pi times radius. That's actually a more useful form, as we'll find in a few minutes. How big is pi? Well, pi is an irrational number approximately equal to this decimal. And in fact, that decimal goes on forever. There's no repeating pattern. It just goes on forever. If we locate pi on the number line, notice it's very close to 3. It's between 3 and 4, relatively close to 3. In rough approximations, very rough approximations, we can simply approximate pi as 3. And if we need a slightly better approximation, we can use 3.14 or 22 over 7. That's actually a very useful approximation for pi. We can also talk about pieces of a circle. The highlighted curve from A to C is called an arc. So that is a piece of all the way around the circle. Technically, if we said arc AC, that would mean the short route around the circle, but the test is usually very careful to say arc ABC, to specify a 3-letter name for the arc, and that way it makes it clear that we didn't go the other way through point D. Finally, we can talk about the area of the circle. This famous formula was discovered by the brilliant mathematician Archimedes. Archimedes was really one of the greatest mathematicians of all time, and his formula is area equals pi r squared. We notice that the area formula is in terms of the radius. We can also express the circumference in terms of the radius. So what that means is, if we know the radius of a circle, we can find out all its other values. This indicates a primary strategy for circle problems. Whatever you're given, find the radius first, and then use the radius to find whatever else you need. That is a really important mindset to have when you're dealing with circles. Here's a very simple practice problem. Pause the video and then we'll talk about this. Okay, the area of a circle is 28 pi. What is the circumference? Well, set that area, 28 pi equal to pi r squared, cancel the pi's, we get r squared equals 28, or r equals the square root of 28. Now, of course, we can simplify that to 2 root 7. The circumference equals 2 pi r. So 2 pi times 2 root 7, that would be 4 pi root 7. And that is the circumference of the circle. In summary, all radii of a circle are the same length. A chord is a segment that has both endpoints on the circle. A diameter is a chord through the center. This is the longest possible chord in a circle. Of course, the diameter equals 2r, so that means that we can express the circumference either as pi d or as circumference equals 2 pi r. An arc is a piece of the curve of a circle denoted on the test by 3 points. Area equals pi r squared. And the number one circle strategy is find the radius first and use the radius to find everything else.
Circle properties. In the previous lesson, we covered some of the basics. We covered radii, chords, diameter, circumference, the famous formula for circumference, and the famous formula for area. Now, if any of those are brand new to you, I suggest watching that previous lesson on circles. In this lesson, we're going to talk about something different. In this lesson, we're going to explore several ideas involving angles in circles. The first is probably obvious. Any triangle with two sides that are radii has to be isosceles. So, for example, AOB has to be an isosceles triangle because OA and OB are radii. And, of course, all radii to the same circle are equal. So that would mean that the two base angles are equal. So angle B would have to be 70. And the angle in the middle would have to be 40 degrees. If the chord side of such a triangle is also equal to the radius, then the triangle would be equilateral. So in other words, if we have a chord EF that has the length equal to a radius, then when we draw that triangle, all three sides are radii. So we get an equilateral triangle. All the angles are 60 degrees. And notice that that angle EOF, that angle is at the center of the circle. Its vertex, its point, is at the center of the circle. An angle with its vertex at the center of the circle is called a central angle. Now, this is an important idea. The test is not necessarily going to make you know that term, but this is an important idea to understand and understand how it's related to some of the other angles. A central angle has a unique relationship with the arc it intersects. One way to talk about the size of an arc is to talk about its arc measure. In other words, how many degrees it takes up. The measure of the central angle equals the measure of the arc. So here we have a central angle of 135 degrees, so that arc, JKL, that arc has to be 135 degrees also. This is one of the ways to talk about the size of an arc. The other way is arc length, which we'll discuss in the next video. Now, a diameter essentially is a 180 degree angle. It's a straight angle. The degrees of angle AOB would be 180. So it divides the circle into two 180 degree arcs. An arc with a measure of 180 degrees is called a semicircle. The measure of the entire circle is 360 degrees, which is the angle all the way around the circle. If two different central angles in the same circle have the same measure, then they will intersect arcs of the same size. And so if those two angles are equal, then the arcs have to be equal. And in fact, vice versa. If the arcs are equal, then the angles have to be equal also. Similarly, equal chords in the same circle intersect arcs of equal length. So if JK equals LM, then those two arcs are equal. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we have that the arc AB is 50 degrees. And so we want to know not the angle at the center, we want to know the angle at A. What is AOB? Well, first of all, we know that the arc has to have the same measure as the central angle. So AOB equals the measure of the arc, that's 50 degrees. And we know it's an isosceles triangle, so we don't know the angle at A or B, but we know it has to be equal, so we'll call that x. So 50 plus x has to equal 180. Or in other words, 2x equals 130. X equals 130 divided by 2, which is 65. And so that's the measure of both the angle at A and the angle at B. We want the angle at A, so that's answer choice D. Central angles have their vertices at the center of the circle. Another kind of angle has its vertex on the circle. So the vertex of this angle right here is not at the center at all. It's actually sitting on the circle itself. So this is another kind of angle, and this kind of angle is called an inscribed angle. An inscribed angle is an angle that has its vertex on the circle itself. The sides of an inscribed angle are always two chords that meet at that vertex. So here AB is a chord and BC is a chord, and they meet at point B. An inscribed angle also has a special relationship with the arc it intersects. The measure of the inscribed angle is half the measure of the arc it intercepts. So if the angle DEF is 40 degrees, then that arc FGD, has to be 80 degrees. Now, why is this true? Here's one way to see why that's true. Suppose we draw a very special diagram like this. So, of course, arc BC equals the measure of the central angle, BOC. We know that AOB is an isosceles triangle, so angle BAO equals angle ABO, so those two red angles are equal. Just call that X. We know that if we look at the angles forming the radius, forming the diameter, AOC, it must be true that those two angles, the blue angle and the orange angle, have to add up to 180 degrees. So BOC plus angle AOB have to equal 180 degrees. But it's also true in the triangle that the two x's plus AOB equals 180 degrees. Well, look at those two equations. Thing plus AOB equals 180 degrees. Thing plus AOB equals 180 degrees. So in other words, those two things have to be equal. So it must be true that 2x equals angle BOC, and then we can just divide. So x is half the measure of angle BOC, and so it's half the measure of the arc. And so this is one very special way to see why the inscribed angle has to be half the measure of the arc. This means that any inscribed angle that intersects a semicircle, that is, any inscribed angle that has endpoints, that intercepts the endpoints of a diameter, has to be a right angle. So merely the fact that HOJ is a diameter automatically means that K has to have a right angle because it's intersecting an arc at 180 degrees. And the test absolutely loves that fact. It really loves to draw this kind of diagram and expect you to know that that is a right angle. If two inscribed angles in the same circle intercept the same arc or the same chord on the same side, then those two inscribed angles have to be equal to each other. So here those two angles, LNM and LPM, those two angles are equal. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we're given angle BEC's 20 degrees. So we know right away that that arc BC, has to equal 40 degrees. Well, we're told that BC equals CD, so we know that arc CD also equals 40 degrees. So the arc from B to C to D is 40 plus 40, or 80 degrees. Arc BD is 80 degrees. That's the arc that angle A intercepts. So A has to be half that arc, or 40 degrees. Finally, we'll discuss a line outside of the circle. A tangent line is a line that passes by a circle and touches it only at one point. Tangent from the Latin tangere, to touch. And in fact, we get the English word tangible from this same Latin root. So a tangent line simply touches the circle at one point. If we draw a radius to the point of tangency, the radius and the tangent line are always perpendicular. That's a really important fact, and the test loves that fact too. Notice that this lends itself to the Pythagorean theorem and other special right angle facts. And so there's all kinds of things that can be implied once you have a right angle. Here's a practice problem. Pause the video and then we'll talk about this. So this is a complicated diagram, but it's actually not too hard of a problem. First of all, notice that angles PQS, this angle here, and this angle PRS, they intersect the same chord, the chord PS. And if two angles intersect the same chord, they have to be equal. So that means that PRS has an angle of 40 degrees. Well, now look at the angle at S. We know that PR is a diameter. And this is an PSR is an angle inscribed in a semicircle. So that has to be a right angle. So PSR is 90 degrees. Well, now if we just look at the triangle PSR, we have the angle at R, we have the angle S, we can find the angle at P. The angle at P has to be 50 degrees. Then we know that TPO is a right angle because TP is a tangent line and it has to be perpendicular to the radius. So TPS, the angle that we're looking for, equals TPO minus SPR, which is 90 minus 50, or 40 degrees. And we choose answer choice C. In summary, if two sides of a triangle are radii, the triangle is isosceles. A central angle has the same measure of the arc it intercepts. Equal chord lengths intercept equal arcs. An inscribed angle has half the measure of the arc it intercepts. An angle inscribed in a semicircle is 90 degrees. Two inscribed angles intersecting the same chord on the same side are equal. And finally, a tangent line is perpendicular to a radius at the point of tangency. Now we can talk about arcs and sectors. In the previous lesson, we said that arc measure, the number of degrees in an arc, was one way to talk about the size of an arc. As long as we are looking at two arcs in the same circle, arc measure is adequate to compare the size of two different arcs. If we start comparing arcs in different size circles, it becomes clear that arc measure alone is not sufficient. The two arcs have the same measure, 30 degrees, but they are not the same size in every way. Clearly, from C to D is a much larger distance than from A to B. So they have two different lengths, even though they have the same measure. How do we find the length of an arc? The length is called the arc length, and it is found by setting up a part-to-whole proportion. Remember that a proportion is an equation of the form fraction equals fraction. So we're going to have part over whole equals part over whole. One part over whole is going to be the arc length. The arc length is part of the circumference, so it's going to be the arc length over the circumference. The other part is going to be the arc measure, or the measure of the central angle, and that's part of 360 degrees, which is all the way around the circle. So it's going to be arc measure over 360 degrees. And so writing this out, we get this, and of course we've just subbed in the formula for the circumference of a circle, 2 pi r. So that is a good proportion to know. And again, don't just memorize this. Make sure you understand why we're doing part to whole with both the lengths and with the angles. So for example, in this circle, 120 degrees is a third of 360. So arc AFB must be a third of the whole circumference. So the whole circumference, 2 pi r, is 48 pi. Well, a third of that would be 16 pi. Here's a relatively easy practice problem. Pause the video and work on this. Okay, if the length of arc CDE is 12, then find the area of the circle. Well, first of all, let's think about that. 72 over 360. We don't need a calculator for this. 72 is 2 times 36, and 360 is 10 times 36. Cancel the 36's. We just get 2 over 10, or 1/5. This is 1/5 of a circle. So the circumference would just be 5 times that arc. 5 of those arcs would make the circumference. So 5 times 12 pi, which is 60 pi. And of course, that has to equal 2 pi r. So if we solve that, divide by pi, divide by 2, we get the radius equals 30, just 30. Now we can find the area. Area equals pi r squared. Pi times 30 squared. 30 squared is 900. So the area is 900 pi. Just as we can divide the circumference into fractions, we can divide the whole area of the circle into fraction. So a slice of the circle like this is called a circular sector. And so a sector is like a slice of pizza. And we could even say that the arc length is like the crust of the pizza. So that circular sector has an area. We could find the area of the sector by setting up another part to whole proportion. So we're still going to have central angle over 360, but now we're going to have area of the sector over area of the whole circle, pi r squared. We equate the ratio of the areas to the ratio of the angles. So that's the formula for the area of a sector. And again, don't simply blindly memorize. Make sure you understand how we got this. So for example, in this circle, we know that 60 over 360 is 1/6. Area equals pi r squared, which is 18 times 18. I'm just going to leave it like that. If we divide that by 6, we get 3 times 18. 3 times 18 is 54. So the area of that shaded sector is 54 pi. Here's a hard practice problem. Pause the video and then we'll talk about this. Okay, we're told the diagram is not drawn to scale. We know the radius of the circle, it's 8, and we know the area of that sector. That sector has an area of 16 pi. And notice that we want the length of JLK. JLK is this arc all the way around the circle. All right. Well, because we know the radius, we can find the area. The area of the circle, pi r squared, is 64 pi. That's the area of the whole circle. So how much of that whole circle is this sector taking up? It's taking up a quarter of the circle. Well, that's interesting. That means that the central angle has to equal 90 degrees. We're told the diagram's not drawn to scale. It certainly is not. JOK is, in fact, a right angle. And so that sector is a quarter of the whole circle's area, and the arc length has to be a quarter of the circumference. Well, the circumference is 2 pi r, or 16 pi, a quarter of that. Well, the quarter, this part here, JK, that has a length of 4 pi, but we're not looking for that. We're looking for all the way around the circle, 3/4 of the circle. 3/4 of the circle is 12 pi. So we go back to the answers and choose answer choice C. In summary, we find arc length and area by setting up similar part to whole proportions. In both cases, we're setting up the proportion equal to a proportion of angles. So arc length is part of the circumference. It equals angle over 360. Area of a sector is part of the area of the circle, pi r squared, and that equals angle over 360.